Okay, listen carefully. Remember, if we had 4 grams of helium, we'd have the same number of atoms as if we had 20 grams of neon. The same number of atoms, because these are the relative masses of these elements. Neon's more massive than is helium. If you want the same number of neon atoms as helium atoms, you got to weigh out 20 grams of neon and only 4 grams of helium, and you'd have the same number of each. You'd have the same number of each. What is that number that you would have? Would that number be a very small number, or would it be a very large number? Let's see, if you had 4 grams of helium and 20 grams of neon, well, we know atoms are really, really small. So if you had 4 grams of a material, you're going to have a lot of atoms, right? So the number of atoms you're going to have in 4 grams of helium is a very large number. The number of atoms you're going to have in 20 grams of neon is going to be a very large number. And they would be the same number, 4 grams of helium and 20 grams of neon. But what would that number be? I'll tell you. If you had 4 grams of helium, 4.003 grams of helium, the number of helium atoms in there are 6.02 times 10 to the 23rd. This is a very large number. That's 10 to the 23rd. That's a lot of zeros. This is like a billion trillion, something like that. Remember, the atoms are so small, you're going to have this many in any macroscopic amount. No, not any macroscopic amount, 4.003 grams of helium. Oh, if you had 20.180 grams of neon, you'd have that same number. You'd have 6.02 times 10 to the 23rd neon atoms. What have we done here? We've taken the atomic masses and we've expressed them in units of grams. And when you've done that, the number of atoms you have in that mass equals this particular number, 6.02 times 10 to the 23rd, which is a very, very, very large number. Oxygen. If you had 15.99 grams of oxygen, you'd have 6.02 times 10 to the 23rd oxygen atoms. You know, just look at the periodic table and at any element, look at its atomic mass and express that mass in units of grams, and you're going to have the same number. Ooh, how about iron? Iron has an atomic mass of 55.845. Express that in grams. You know how many iron atoms you have in that sample? The same, 6.02 times 10 to the 23rd. How do we get this number, 6.02 times 10 to the 23rd? Well, let's look at it. If you had 4 grams, 4.003 grams of helium, you want to know how many helium atoms are in that sample of 4 grams. You know what you need to know first? You would need to know the mass of one single helium atom. You know, it wasn't until the early 1900s that techniques were developed to measure the mass of single atoms. And after they were able to do that, they were able to do this calculation. I'm going to give you here the mass of a single helium atom. One helium atom has a mass of 6.64 times 10 to the minus 24th grams. That's a very, very small number. Remember, we're talking about only one helium atom. Okay, if one helium atom has that mass, we should be able to calculate the number of helium atoms in a larger mass, 4 grams. So what we do is we take the 4.003 grams and we multiply it by this ratio. And note the units of grams cancel out and we're left with units of atoms of helium. And here we go. The answer is 6.02 times 10 to the 23rd atoms of helium are in 4.003 grams. But in order to get that calculation, we had to actually experimentally measure the mass of a single helium atom. Let's do the same calculation for iron. Iron has an atomic mass of 55.845. Now, let's see, if we have 55.845 grams of iron, we want to know how many iron atoms are in there. We're going to need to know the mass of a single iron atom. Well, you know it's going to be correspondingly more massive than the mass of a single helium atom. So the number down here is going to be a larger number than up here for the helium, and indeed it is. 9.28 times 10 to the minus 23rd is greater than 6.64 times 10 to the minus 24th. Why? Because iron atoms weigh more than do helium atoms, and correspondingly so. And so let's calculate the number of atoms in this mass of iron. The grams cancel out, and we're left with the number of iron atoms, which is the same number. 6.02 times 10 to the 23rd atoms of iron are in 55.845 grams of iron. It's always the same number. We call this number Avogadro's number in honor of Avogadro. Recall back in chapter 3, he was one of the pioneers of atomic theory. And Avogadro's number is 6.02 times 10 to the 23rd. And when you express the mass of a material, its atomic mass, in units of grams, you have Avogadro's number's worth of those atoms. This number might look familiar to you. It's also known as the mole, which we introduced in an earlier chapter. Avogadro's number is equal to 1 mole. So if you have 4.003 grams of helium, that corresponds to 1 mole of helium. 55.845 grams of iron corresponds to 1 mole of iron. So the atomic mass of an element expressed in grams is equal to 1 mole of that element. 207.2 grams of lead is 1 mole of lead. That's 6.02 times 10 to the 23rd atoms of lead. So this is for atoms. We can do the same sort of thing for compounds. The formula mass of a compound expressed in grams is equal to 1 mole of that compound. Water, H2O, it has a formula mass of 18 AMU. Express the 18 in units of grams, and you will have 6.02 times 10 to the 23rd molecules of water. That's 1 mole of water. 18 grams of water equals 1 mole of water. And you know 1 mole of water is 6.02 times 10 to the 23rd molecules of water. Now we can define what we call molar mass. The mass of 1 mole of a substance. Lead, molar mass is 207.2 grams. The molar mass of water is 18 grams. Another way to put that would be 207.2 grams per mole. In 207.2 grams, you've got 1 mole. Likewise for the water, in 18 grams, you have 1 mole. Now I have some samples to show you. What I've got here is 207.2 grams of lead. Take a close look. 207.2 grams of lead. This is a molar mass of lead. How many lead atoms are in here? 1 mole of lead atoms. That's 6.02 times 10 to the 23rd lead atoms. What I've got here is 1 molar mass of water. There's 18 grams of water in there. How many water molecules are in there? 1 mole of water molecules. That's 6.02 times 10 to the 23rd water molecules are inside that 18 grams. You know, we didn't count out those atoms one by one till we got up to 6.02 times 10 to the 23rd. No, we didn't have to do that. We knew their relative masses from the periodic table, and all we had to do was measure out their masses on a scale. 207.2 grams of lead, that corresponds to 1 mole of lead atoms. 18 grams of water, that corresponds to 1 mole of water molecules. These are the molar masses of these materials. Okay, let's see an application of this. This is the chemical equation we've been working with, the reaction between carbon and oxygen to give rise to carbon dioxide. Look at these coefficients here. Remember, we need, for every 1 carbon atom, we need 1 oxygen molecule. How about if we were to have 1 mole of carbon and react it with 1 mole of oxygen? Recognize that's a 1-to-1 ratio by number. What would it be by mass? Let's see, you know, the mass of 1 mole of carbon is 12, and so that's going to be 12 grams. And likewise, the mass of 1 mole of O2 is 32 grams. Got that? So either way you put it, it's the same thing. 1 mole of oxygen or 32 grams of oxygen, O2, that's the same number of atoms. And over here we've got carbon dioxide, 44 grams, okay? And that corresponds to 1 mole of carbon dioxide. The formula mass of carbon dioxide is 44. Now, that's the same thing as saying 6.02 times 10 to the 23rd atoms of carbon, which is 12 grams of carbon, which is 1 mole of carbon. Same. Over here, for the oxygen, 1 mole is 6.02 times 10 to the 23rd molecules, and 1 mole of CO2 is 6.02 times 10 to the 23rd molecules. You see, we have a 1-to-1-to-1 ratio by number. Here's 1-to-1-to-1, or 6.02 times 10 to the 23rd to 6.02 times 10 to the 23rd to 6.02 times 10 to the 23rd. You know, that's why we don't say 6.02 times 10 to the 23rd, because it's a mouthful. And we instead say 1 mole to 1 mole to 1 mole. Remember, the mole is a measurement of numbers of atoms or molecules. And so it's a very convenient concept to use, the mole concept. Hey, let's look at it for water. For water, we're going to have 2 moles of hydrogen react with 1 mole of oxygen. It doesn't have to be a 1-to-1. Now you understand moles, you can do whatever ratios the coefficients dictate. Here we've got 2 units of hydrogen, 2 molecules of hydrogen. So that means we'd need 2 moles for every 1 mole of oxygen. This is a 2-to-1 ratio by number. By mass, it's a different story. Let's see, it's 4 grams to 32 grams. But by number, recognize it's a 2-to-1 ratio. And we could calculate the number of molecules, if you're willing, there. And here's the whole point. When you cook in the kitchen, you see, you look to your recipe to find out how much of the ingredients that you need. What does a chemist do? A chemist is wanting to do a chemical reaction. What he or she does is looks to the periodic table. And in that periodic table, they'll get the relative masses of the various elements, or the ingredients, if you will, the reactants for the reaction. And so they can measure out the quantities that they need. Chemistry and cooking are a lot alike. The cook looks by the recipe. The chemist will look to the periodic table. Good chemistry to you.